Hello everyone, it's Mr. Wolfe here, and in this video I'm going to be introducing the concept of mass versus weight. All right, so these are two variables that are really closely linked together, but it's really important to realize that they are two different things, and it's really important to understand those differences. So, mass is going to be just the amount of stuff, the amount of matter in an object. Right. So imagine I have an object maybe like this big, and it is made up of, let's say, helium. So pretty light, right? So really we could say it doesn't have that much mass, at least compared to maybe an object maybe the same size, but it's made up of lead. So those atoms have much more mass to it. There's much more stuff in that same amount of area, so we would say that it has more mass. Right? So it's the amount of matter in an object. I always like to sometimes just say, or more of like a simple definition, the amount of stuff an object has. These are the same definition. This one's just a little bit more technical. All right, so these are things that mass is not. It is not volume. And it is not weight. All right. So line down the middle right here, definitely related to these two, but mass is not weight. Super important. All right. Our unit of mass is going to be, and we've talked about this before, kilograms. kg stands for kilograms. All right, so that's mass. How is that different than weight? All right. So weight is going to be the same exact thing as the force of gravity. Force of gravity, weight, same thing. So force of gravity on an object. Right. So it's determined by this variable called g. Right. So g is over here, right? And that stands for the gravitational field strength. Gravitational field strength. Right. Really all this is just a measurement of the pull, the gravitational pull of a certain planet. And so it differs whether you're on the Earth, right, G's this, whether you're on the moon, or whether you're on Jupiter. Right? So that brings up a few important points, is that if we're talking about mass, the mass of an object is the same regardless of location. All right. So let's say you're on Earth, or in this case, Tim is on Earth. Tim has 75 kilograms worth of mass. But let's say we take Tim and we put him on the moon. Tim should still have the exact same mass, right? The amount of stuff in Tim hasn't changed. The only thing that's changed is his location. Right? So I might even just draw this line a little bit further down just to separate these two things. All right, so let's go back to weight here, and we're going to compare and contrast. But first, our unit of weight is going to be, well, if it's my force of gravity, well, force is measured in newtons, abbreviated by a capital N. But here's the big thing I want to get to, is that mass, right, does not change regardless of location. Right? But I could say, and I'm going to star this too, is that weight slash force of gravity, because they're the same thing, changes depending on g. So it changes depending on g, and remember, g is just the gravitational field strength of each location. Right. So if I'm on the Earth, right, with a G of 9.8 newtons per kilogram, All right, or if I'm on the moon, notice that that gravitational field strength is less. That kind of makes sense. Gravity's less on the moon. That's why you can jump higher. And then on Jupiter, it's a really, really big gravitational field strength because it's a really, really big planet. And so your weight on each of these planets is going to be different. Right? But if you're the same person on at any of these locations, you're going to have the same mass. So let's use these conceptual concepts of mass versus weight and apply it with an equation. So our equation is going to be, it's actually right up here, Fg, or your weight, is going to be equal to your mass. So mass and weight definitely related, because we could see that with the equation, and they're directly related. If your mass goes up, your weight goes up. Right? But it's going to be mass times the gravitational field strength. Remember how much a planet is going to be pulling on you, depending which planet, which location you're at. So let's apply the equation. What is the weight of Tim on Earth? So we got mass in kilograms, right? And I have my gravitational field strength. So let's first just write our equation. Fg is equal to mg. Right? I'm looking for the weight, so this is going to still just stay in variable form. My mass in kilograms is 75, and my gravitational field strength on Earth, you will become I got to move this up. You'll become very, very familiar with this number, is 9.8 newtons per kilogram. So when you do the math on this, you find that F of G is 735 newtons. So that's the weight. Right? So to put this into perspective, by the way, 735 newtons would be the same thing as a 165 pound person. So you're used to seeing the unit of a force or weight in pounds, and newtons is just a different way to represent it. It's how we represent it with the metric system or in physics. All right. So now let's look at another problem. What is the weight of Tim on the moon? So still going to use the same exact equation. Fg is equal to mass times gravitational field strength. And I'm looking for weight. And let's see, the information that I'm given up to here is the gravitational field strength, which is less than that of Earth. So I should automatically expect my force of gravity to be less as well once we find it. 3.67 newtons per kilogram. But it doesn't give me the mass in this problem. So then I have to kind of think about what would the mass be. Right? And that's where I'm going to use my understanding of mass over here. If Tim's mass is 75 kilograms on Earth, the amount of stuff in Tim, as long as he still has all his arms and legs, is still going to be the exact same on the moon. It's going to be 75 kilograms. So if I know that, I could just say, oh, same mass, 75 kilograms. So I'm going to plug that into my equation. And when you do the math on this, you're going to get the force of gravity on the moon is going to be 275.25 newtons. Right. And to put this into perspective, if this is how much he would weigh on the moon and he was 165 pounds on Earth, he would only weigh 60 pounds on the moon because gravity is there's just a smaller gravitational field strength pulling him towards that big object, the moon. All right, so let's look at the last problem. What is the mass of Jennifer if she weighs 1,820 newtons? So I'm going to use my same equation, and notice here I'm looking for mass, and this time I'm given my weight, so 1,820 newtons. So I got to make sure that I'm plugging in my numbers to the correct variable, and I could always you could say weight. Well, weight is the force of gravity, but I could also look at my unit, newtons, right? That's going to go here too. And then I'm going to look at the gravitational field strength of Jupiter, and it's big, 26 newtons per kilogram. All right. So then when you do the math on this, right, you're going to get that her mass is 70 kilograms. Right? So one thing you might be wondering is, Mr. Wolfe, you said that mass doesn't change, right? And it doesn't, right? But notice that before we were looking at Tim, he didn't weigh. His mass was 75 kilograms, and now we have a different person, Jennifer, right? So if I were to take Jennifer, and Jennifer's mass is 70 kilograms, if Jennifer would go over to the moon, her mass would still be 70 kilograms. And if she went over to the Earth, her mass would still be 70 kilograms. So as long as it's the same object, mass is not going to change.